Hello viewers, we will begin complex integration. So, the properties of analytic functions are very much related to integration of complex functions. So, the complex integration actually brings out the properties of an analytic function. So, to begin with, we will consider an integral of a certain type. Okay. So, complex integration. Let f from let us say a b to c. Here a b is a closed and bounded interval. Okay. It is a subset of real numbers, of course. Let this be a continuous function. Okay. And let f of t, now f is a function of one real parameter t. So, let f of t be separated into its real and imaginary parts in the following way. It is a complex valued function. So, let it be u of t plus I v of t for t between a and b. Okay. And then let us define the definite integral of f of t dt, okay, in terms of the definite integral that we already know from one variable calculus. So, let this be defined as the integral from a to b of u of t dt plus I times the integral, the definite integral a to b v of t dt. Okay. So, it is defined in terms of the Riemann integral that we already know. Okay. And let us see some quick simple minded examples. So, consider f of t equals t cosine t plus I times t sine t, okay, and t ranges, let us say, between 2 pi and 4 pi. Okay. So, then let us calculate the integration 2 pi to 4 pi of f of t dt. Okay. And so, compute this. So, this integral by definition is the integral from 2 pi to 4 pi of the real part of f, which is t cosine t dt plus I times the integration of the imaginary part of f, which is t sine t dt. Okay. And we can integrate these functions by using parts. Okay. So, t cosine t, the integration of this will be t sine t, the integration of cosine t is sine t. Okay. So, between the limits 2 pi and 4 pi minus the integration of the differentiation of t is 1 times the integration of cosine t is once again sine t dt between the limits 2 pi and 4 pi. That is for the real part, plus I times the imaginary part. The integration of imaginary part is once again by using integration by parts. So, the integration of t sine t is t times negative cosine t, which is the integral of sine t. So, you have minus t cosine t between the limits 2 pi and 4 pi minus the integration of the differentiation of t is 1 and the integration of sine t is minus cosine t dt well between 2 pi and 4 pi. So, the integral from 2 pi to 4 pi. So, this gives you sine t is 0 either at 4 pi or 2 pi. So, so this piece vanishes, okay, and then minus the integration of sine t is negative cosine t. So, you get positive cosine t minus times minus is a plus. So, between 2 pi and 4 pi plus I times once again here you get minus 4 pi cosine 4 pi is 1 minus. So, you get a plus 2 pi times cosine 2 pi is 1, okay, and then minus the integration, well, this is a plus integration of cosine t is sin t between 2 pi and 4 pi, and that is a 0, okay, because sin is 0 at 4 pi or 2 pi. So, you get cosine t between 4 pi and 2 pi, well, that gives you a 0 again. So, this is again a 0 plus I times minus 2 pi plus 0. So, that gives you minus 2 pi I. Okay. So, using integration by parts, we can find out or compute this definite integral. Okay. So, here is another example. Let me give this as an exercise to the viewer. Okay. So, let m and n be integers. Let m and n be integers. Okay. Show that the integral 0 to 2 pi e power I m t times e power minus I n t dt is 0 or 2 pi, 0 when m is not equal to n and 2 pi when m is equal to n. Okay. So, it is an easy exercise using the definition, okay, and this property actually makes these functions e power I m t the orthonormal basis modulo some constant. Okay. It makes this these an orthonormal basis for a certain vector space. I mean, this particular property makes it an orthonormal basis. Okay, but that is an aside, that is not directly related to this topic here. Okay. So, next what we want to do is we have seen this type of integral. Next what we want to do is define what is called a contour integral. So, roughly speaking, if we have a complex function, a complex valued function of a complex variable, then we would like to define its integral over a piece of string or a curve in the complex plane, where the curve has certain properties. Okay. So, it is a directed curve and there are some other properties. So, what we really formally call this curve is a contour. So, we define the integration of a complex function on an entity called a contour. So, in order to make the definition, first I need to discuss what a contour is. Okay. So, here is a contour. Okay. So, contours in C. So, a curve. So, we will start with what is a curve. A curve gamma, okay, with parameter interval a comma b, okay, is a continuous function gamma from a b to c. Okay. So, we are defining a curve with. So, let us look at another example. Gamma 2 of t equals t plus I sin 2 pi t. T ranges, let us say, between 0 and 1. Okay. So, well, gamma 2 of 0 is 0 plus I sin 0. Okay. So, you get 0. Okay. Okay. So, this is so this starts at 0 and gamma 2 traces the sine curve in the complex plane, okay, where the real axis is acting as the x axis for the graph of the sine curve. So, you get sine curve like that when t equals, for example, 1/4, you get 1/4 plus I sine pi by 2 and you reach 1/4 plus I, okay, and gamma 2 at half, for example, gives you half plus I sine pi. So, you are at the point half on the real line, etc. So, gamma 2 at 1 will give you 1 plus I times 0, which is 1. Okay. So, gamma 2 starts at the origin in the complex plane, okay, and at time t equals half, you are at this point here. This is, or 1/4 rather, you are at this point 1/4 plus I, okay, and at time t equals half, you are at this point half plus 0, I mean half on the real line, okay, and at time 3/4, for example, you are at this point 3/4 plus, or rather minus I, 3/4 minus I, and finally, at the time 1 you reach this point 1. Okay. So, the particle starts here and travels as dictated by gamma 2, okay, this way, and it ends up at this point 1. Okay. And using this very example, we can construct yet another example. Gamma 3 of t, let us say, is 1 minus t plus I sine 2 pi times 1 minus t. Okay. T ranges from 0 to 1 again. Okay. So, when we try to trace gamma 3 by this definition is a curve with parameter interval 0 1 already. Okay. But when we try to look at the picture, when we try to visualize this gamma 3, we get this very same sine curve, except that it now starts at gamma 3 of 0 is now 1 plus I sine 2 pi times 1 minus 1, which is 0. So, this you get is 1. So, now it starts at 1, okay, and when gamma 3 is at 1/4, okay, you get 3/4 minus I. So, it goes this way, okay, this is 3/4 minus I at 1/4 at time t equals 1/4, etc., and then you go backwards. At time half, you are here again half, okay, and then at time 3/4 you are at 1/4 plus I. Okay. So, gamma 3 of 3/4 is now 1/4 plus I, and then finally, at t equals 1, you are at 0. Okay. So, gamma 3 is, I mean, has the same range as gamma 2, okay, in the complex plane, but it is traced in the opposite direction. Gamma 3 dictates the particle to travel in the opposite direction to that of gamma 2, of the curve gamma 2. Okay. So, we already see that when you give a curve with a parameter interval, it comes with a direction associated with it. Okay. When you look at the range of the function in the, when you look at the range of the curve gamma in the complex plane. Okay. So, let us say that in words, a curve, okay, has an induced, okay, a curve over a parameter interval, okay, has an induced direction due to the increasing value of the parameter, okay, in its parameter interval. Okay. So, you have a parameter interval for a curve, and when the parameter increases in that parametric interval, that gives an induced direction on the curve. Okay. So, here graphically or visually that direction refers to the direction of the curve of the locus or the range in the complex plane. The set which is the range, okay, the set gamma star equals set of all gamma of t such that a less than or equal to t less than or equal to b, okay, is called the image, okay, of a curve gamma over the parameter interval a b. Okay. And we say that gamma is contained in a set S, okay, set S, which is a subset of the complex plane. Okay. So, we say gamma is contained, gamma is a function, remember, but we use the terminology gamma is contained in a set to mean when gamma star, which is its range, is contained in S. Okay. So, if the range is contained in S, we say gamma itself is contained in S. That is just a way of saying it. Okay. And then a curve gamma, okay, over a parameter interval a b has gamma of a, okay, which is a complex number, okay, which is in the complex plane, okay, as its initial point, okay, and gamma of b as its final point. So, we will use these words initial point and final point to mean gamma of a and gamma of b given a curve gamma. Okay. And because there is an induced direction, okay, given a curve gamma with the parameter interval a comma b, the opposite curve, okay, minus gamma. So, we are calling the following as opposite curve, and we denote it by minus gamma, okay, with the parameter interval, the same parameter interval, okay, is the curve defined by minus gamma of t is gamma of a plus b minus t, where t ranges from a to b. Okay. So, minus gamma is defined as gamma of a plus b minus t. So, in the above example, let me go back, sorry. Okay. So, in this example here gamma 3 was the opposite of gamma 2, okay, because gamma 2 is traced in this direction, okay, whereas gamma 3 is the same has the same range, okay, and is traced in the opposite direction. Okay. So, due to that geometric significance, we want to define the opposite curve in this fashion, okay, and please note that minus gamma of t is not minus of gamma of t. if gamma of t is a complex number, if you consider that complex number gamma of t, it is not the same as minus gamma of t is a new function. Okay. It is not the same as minus of gamma of t. Okay. It is actually defined here, it is gamma of a plus b minus t. Okay. So, you have to be careful. So, essentially visually it is clear what we want to say, it is essentially the same range traced in the opposite direction. So, it has an opposite implied direction to that of gamma, okay, and the parameter interval stays the same. Okay. And so, gamma 3 in the above example is minus gamma 2. Okay. So, now we want to make some more definitions here, some more terminology is due here. A curve gamma with parameter interval a b, okay, is closed. We want to call it closed if gamma of a is equal to gamma of b, i.e., its initial point in the complex plane is equal to the final point. Okay. And it is called simple, the curve, okay, the curve gamma with parameter interval a b is called simple, okay, if gamma 1 of t, or rather gamma of t 1 is not equal to gamma of t 2 unless t 1 is equal to t 2, or in the case of a closed curve, of course, the end points are equal, okay, the initial and final points are equal. So, you want to allow this gamma of t 1 equals gamma of t 2 when t 1 equals a and t 2 equals b. Okay. So, apart from these cases, gamma of t 1 should not equal gamma of t 2. Okay. What this means essentially is that if you look at the range of gamma, okay, a curve is called simple if it does not have self intersections, the range does not have self intersections, okay, except that the only intersection you will allow is possibly that the initial point is equal to the final point, that is okay. Okay. So, that is called a simple curve. Okay. So, let me say no self intersections, okay, except at the end points is simple. Okay. So, here is visually a simple closed curve, or rather simple non closed curve. Okay. What this really is in the complex plane is it is the range of a simple non closed curve, okay, but I am abusing the notation and terminology here, and I am calling it the range itself as a curve. Okay. So, maybe there is a direction. Okay. So, likewise, if you have the range is something like this, a circle or an ellipse or some kind of curve like this, where the initial point meets the final point, this is a simple closed curve. Okay. And something like this, where the initial point is not equal to the final point and there are self intersections, is a non simple non closed curve. It is non closed is clear, the initial and final points are not equal. It is not simple because there is a point of rather point of intersection. Okay. And likewise, here is a curve, okay, which is closed, okay, a non-simple closed curve. So, all these are actually ranges of certain curve with some parameter interval. Okay, so, they come with some direction, okay, but yeah, I am going to call the visualization of them as curves. Okay. So, now just for motivating the definition here, okay, of simple and closed. Okay. So, now let gamma 1 be a curve, okay, with parameter interval a comma b, okay, and let gamma 2 be a curve with parameter interval C D, let us say. Okay. Now, what we want to do is sort of join these two curves when it makes sense. So, suppose you have a range of gamma 1, which is some piece of string sitting inside the complex plane, and gamma 2 starts where gamma 1 ends, okay, and suppose that it continues from there, okay, and it is another piece of string. What you want to do is define a join of these two. Okay. So, so here is what we will do to define the join. Okay. When the final point of gamma 1 is the same as the initial point of gamma 2, okay, i.e. gamma 1 of B in this case is equal to gamma 2 of C. Okay. Then we define, okay, we firstly we define the join of gamma 1 with gamma 2, okay, as, so this is the notation gamma 1 plus gamma 2 to mean the join of gamma 1 and gamma 2. So, gamma 1 plus gamma 2 of t, this is defined as gamma 1 of t for t ranging from a to b. Okay. So, for the first part of the time, t is like the time parameter. For the first part of the time from a to b, we describe gamma 1, okay, and for the rest of the time, okay, we will decide what that is. For the rest of the time, we will trace gamma 2. Okay. So, we will we want to start at b. Okay. Now, time has to continue where it has left off. So, we want to start at b, okay, and end where? Well, we have the parameter interval for gamma 2 to be of length d minus c. Okay. So, we want to end at b plus d minus c. Okay. So, here is an interval of length d minus c which starts at b. Okay. So, we have actually added, okay, so what we have done is we have added d minus c to both sides of this kind of equation, or rather we have added b minus c to both sides of this kind of inequality. Okay. So, to compensate, we will do the following: we will subtract b and add c to the parameter of gamma 2. Okay. So, then for this time interval, which is actually a translation of the interval c d, okay, which is a translation of the interval CD, gamma 2 will be traced. Okay. So, the join is just a slight modification. You first travel along gamma 1, the range of gamma 1, okay, and then you trace gamma 2 from there on. Okay. So, that is a join. So, note that the join itself is a curve with parameter interval. Now, A to B plus D minus C. Okay. Then we have done this for 2 curves. Okay. There is no reason why we should stop with 2 curves. If we have n curves satisfying the requirement that the final point of the curve now is equal to the initial point of the next curve, we can construct a join of these n curves. Okay. So, we can likewise define the join, okay, the join of n curves or n curves gamma 1, gamma 2, so on until gamma n, okay, in that order, okay, as long as the final point of gamma I minus 1 is the initial point of gamma I, here 2 less than or equal to I less than or equal to n. Okay. So, what is important is not to get lost in the technicalities here and the symbols here. What is important is to know what these represent, okay, in the complex plane. What we want to do is essentially now want to define the integration of complex function along these kind of joins. Okay. So, we will do an example here. We will try to join 4 curves. Okay. So, here I have let us say this is the real line. Okay. So, on the real line I have minus capital R is some constant, some positive real number, okay, and little r is some positive real number, okay, and then here is r, little r again, okay, and then capital R again. Okay. So, I am starting at minus r going until minus little r, okay, and then tracing this little circle here, okay, and going along this straight line from little r to capital R and then back to here, okay, via this semicircle, okay, in the anti-clockwise direction from capital R to capital minus R. Okay. So, let us say let me start here actually, okay, does not matter, let me start here and then go this way, this semicircle, this straight line and then this semicircle in the clockwise direction. Okay. So, this is the curve I want to describe. Okay. So, I can realize this as a join of 4 curves. Okay. So, gamma 1 of t, okay, I will start here from little r and go until capital R. Gamma 1 of t, I can write this as r times 1 minus t plus r t. Okay, this is a linear equation where t goes from 0 to 1, okay, and that describes a straight line, of course. Okay, and then gamma 2 of t is now this semicircle in the anticlockwise direction. So, gamma 2 of t, let me write that as capital R e power I t, where t goes from 0 to pi. 0 to pi gives me a semicircle, okay, and in the anticlockwise direction we have R e power I t, okay, and gamma 3 of t is the straight line, okay, is the straight line there, which starts at minus r, okay, and ends at minus little r. So, t goes from 0 to 1, and gamma 4 of t is that other little semicircle in the clockwise direction. So, to trace that I have r e raised to minus I t, t going from minus pi, sorry, t going from 0 to pi, or rather minus pi to 0, that is right. Okay. So, we can see that gamma 1, the final point of gamma 1 is the initial point of gamma 2 and etcetera. So, the final point of gamma 2 is the initial point of gamma 3, etcetera. Okay. So, we can construct the join of these 4 curves, gamma 1 plus gamma 2 plus gamma 3 plus gamma 4 of t. Okay. We can construct the join by actually translating these parameter intervals appropriately. Okay. So, let's trace gamma 1. Okay. So, this is equal to r times 1 minus t plus r t. So, let us trace gamma 1 for the time from t equals 0 to 1. Okay. So, for tracing gamma 2, I need to now start at time 1. Okay. So, from time 1, so how long should I go? Well, I should go for a length pi, because for gamma 2 the parameter interval has a length pi. Okay. So, let me go until pi plus 1. Okay. So, then the description of gamma 2 will be r e power I times t minus 1. To adjust for the 1 I have added to this inequality on both sides. Okay. So, when I add 1 to both sides, I get 1 less than or equal to t. Well, t plus pi. So, I am substituting, replacing that with new t, okay, pi plus 1. Okay. And that new t now, for compensation, I will write that as t minus 1 here. Okay. So, let me erase and write that as I times t minus 1. Okay. And then likewise for gamma 3, I should start now at pi plus 1, okay, and go on for a length 1, okay, for an interval length 1. So, t travels from pi plus 1 to pi plus 2. Okay. So, how do we describe gamma 3 now? Well, we will compensate, we will take this equation, or rather this expression, and compensate for the addition of gamma of pi plus 1. Okay. So, then we get 1 minus t minus pi plus 1. So, we get pi plus 2 minus t minus r times, well, t minus pi plus 1. Okay. And finally, we need to trace gamma 4. For that, we should start now at pi plus 2 and pick an interval of length pi. So, we should start at pi plus 2 and then we should end at 2 pi plus 2, because pi plus 2 plus pi is 2 pi plus 2. Okay. And then we trace r e raised to minus I, and then we adjust by subtracting pi plus 2. So, that is your join. So, in practice fortunately, we will not have to construct these joins again and again. We will see there is something which will help us to deal with these joins practically. Okay. But for now, we understand how to join 4 different curves, okay, or n different curves. Okay. Gamma with a parameter interval a b, okay. I want to say when it is considered smooth, okay, I will define smooth, is said to be smooth, okay, if gamma has a continuous non-zero derivative. Okay, on its parameter interval. A b. Okay. So, to avoid pathologies we will need smooth curves. Okay. So, the requirement for a curve to be smooth is threefold. Okay. So, firstly gamma, if gamma is a curve, it is a function. So, gamma prime should be defined at every point in the interval a b, okay, closed interval a b. So, at the end points the definition of derivative needs modification, because you take one sided limits, okay, for a or for b. Okay. In the definition of the derivative you take one sided limits and define the derivative, okay. But nevertheless gamma should be differentiable at every point in the interval. Okay. Not only that, the function gamma prime, when you consider gamma prime as a function, that should be continuous at all points in a b. Okay. And finally, gamma prime should not be 0 at any point in the interval a b. Okay. So, these 3 requirements will make a curve a smooth curve. Also note that this definition of a smooth curve is a difference with the standard definition of a smooth function. Normally a smooth function refers to a function which has derivatives of all orders. Okay. So, here we have differed from that kind of definition of smooth function, okay. And normally what we have defined here is called a regular C1 curve, okay, where C1 here refers to the class of functions which are differentiable and which have continuous derivative, okay, and regular functions are functions which have a non-zero derivative. Okay. But to sum all that up, we have used the word smooth and said that a smooth curve, we redefined the word smooth and said that a smooth curve is a curve which has a continuous derivative and a non-zero derivative as well at each point. Okay. So, please make a note of this. So, that will actually clear many pathologies, okay, because continuous functions, gamma as we defined it, the curve as we defined it is just a continuous function from an interval to the complex plane. Now, a continuous function can be really weird. For example, there are curves called space filling curves, which actually fill up a whole disk, if you wish, starting in an interval a b. Okay. So, continuous functions can be unwieldy. So, we insist that these curves be smooth, so that we can play with them. Okay. And then we will define a path or a contour now. So, at last we have reached where we wanted to be. A path or a contour is the join of finitely many smooth curves. Okay. So, a contour is essentially the join of finitely many smooth curves. Now, when you consider the path or a contour itself as a curve, that need not be smooth, because the points where you join, okay, now you get a new function, join is a function, remember. So, the new function itself need not be differentiable at the points where you join. Okay. But in the meantime, where you have these finitely many smooth curves, okay, in the meantime, depending on the time parameter, it is smooth. Okay. So, so a path or a contour is called a piecewise smooth curve. Okay. So, it's the join of finitely many smooth curves. Okay. So, I will write that in words. Notice that the path, okay, or a path or a contour, a path or a contour, okay, is a piecewise smooth curve with certain parameter interval. Okay. So, depending on how many depending on the parameter intervals for the smooth curves that we are picking to join. Okay. So, and we often assign the standard geometrical terms such as a triangle or a circle, etc., to these contours depending on the range of the contour itself. Okay. So, for example, let me go back to the first example we chose. Sorry. So, here is the first example that we chose. Gamma 1 is 3 plus 2 e power I t. I will call this curve, it is a piecewise smooth curve, sure. Well, it is a smooth curve. Okay. So, I will prefer to call this a semicircular contour. Okay. Or if you pick the following, okay, so gamma of t equals e power I t, which is a circle 0 less than or equal to t less than or equal to 2 pi. Okay. So, it traces the unit circle, gamma traces the unit circle, it starts at 1, okay, goes around in the anticlockwise direction and ends at 1. Okay. This is a circular contour, for example. Okay. So, we will associate the word circular, etc., to these contours depending on the geometric shape of the range of this contour. Okay. So, we can use these contours to define the contour integral of a complex function.